Alright, total internal reflection. Okay, 6.2 total internal reflection. Okay, alright. 6.2 total internal reflection. Okay, so first, what is total internal reflection? So in order to understand what is total internal reflection, we need to look at this incident. Alright. Okay, when light travel from medium of high optical density to medium of low optical density, light refract and bend away from normal. Okay, so this is something that we already learned in the previous topic. Okay, so when light travel from medium of high optical density to low optical density, light will refract and bend away from normal. Why is it that light will refract and bend away from normal? Because when the light go from medium of higher optical density to medium of lower optical density, what happens is the speed will increase. Okay, okay, so light will refract and bend away from normal because the speed of light increase. So glass have higher optical density and also have higher refractive index. Okay, so the refractive index is higher. This one, the refractive index is lower. So what happens is the speed of light here is low. The speed of light here is higher. So what happens is when the speed of light increase, then the light will refract away from normal. So as what you can see from here lah. Okay, this refracted angle is bigger than the incident angle here. Okay. Okay. So there will also be a weak reflected ray. Okay, there is a little bit of light that is reflected inside between this boundary. Okay, a little bit of reflection. Okay, when incident angle increase, refracted angle will also increase. And when incident angle increase until refracted angle reach 90 degree, the incident angle is known as critical angle. Okay, that means like this. This angle, just now, this incident ray just now is here, and the refracted ray is here. But because this angle is bigger than this angle, so that means that when this angle increase, this angle will increase faster and reach 90 degree first before this angle reach 90 degree. Okay? Okay, this angle, the refracted angle will reach 90 degrees. So the incident angle, okay, this angle, when the refracted angle is 90 degree, we call this incident angle as critical angle. Okay, we call this angle as the critical angle. So when this happens, the reflected ray becomes brighter. Okay, this reflected ray is brighter than just now. Okay, brighter than just now. And when critical angle larger, when incident angle larger than critical angle, all light ray will reflect totally into the medium of higher optical density. So all of the light ray will reflect totally into the medium of higher optical density. That means it will reflect back inside. So basically, this reflected ray at first is very weak, and then as the angle increase, the light ray that reflected back inside becomes stronger and stronger until when this incident angle is larger than the critical angle, then all of the light ray will be totally reflected inside. Okay, so this phenomenon where all of the light ray is totally reflected inside the medium is called total internal reflection. Okay, total internal reflection. So you can see why is it called total internal reflection, because although glass is transparent, right? Air is also transparent, but the light, when go from glass into air, it doesn't go into air. Instead, it reflect at the boundary. Okay, it reflect at the boundary, totally go inside. You see, totally go inside here. Okay. Wait, okay, you can see that this one, the refracted angle is increased faster. This one, the incident ray increased slower. But and then this reflected ray becomes stronger and stronger. Okay, you see this one becomes weaker and weaker. This one becomes stronger and stronger. Okay. Okay, until when you see disappear or almost disappear, left a little bit, because this is where the angle become critical angle. Okay, at critical angle. Okay, there's a little bit of light. Okay, a little bit that come out. Here also got a little bit come out. Okay. So this is at the critical angle. This is at the critical angle. And then when increase some more, just a little bit more, then everything, all the light will be totally internal reflected. So this is to mark the critical angle. Okay, this is to mark the critical angle. Okay, the incident angle increase some more, just increase a little bit more, then everything, all the light will be totally internal reflected. Okay, no light will come out from here. Okay, no light will come out from here. All the light will be totally reflected inside here. So this is total internal reflection. Okay, you see all the light reflect here. Total internal reflection. So we mark the light ray, the incident ray. Okay, mark XX like this to mark the path of the incident ray, and here to mark the path of the reflected ray. And then this is the result, okay, that we can get. Okay, so you see, this is the incident. This is the incident ray at the beginning, and then this is the refracted ray. And then when the angle of incident increase until here, okay, increase until here, the light, this one, the refracted ray will slowly go. The refracted angle will increase until become 90 degrees. So the light ray will come out here, okay, 90 degrees. So this here to here, this angle will be critical angle. So increase a little bit more, then all the light will be totally reflected inside the glass. So this angle and this angle will be the same. This angle become a reflected angle, not refracted. This is refracted angle. This one is reflected angle. Okay, different. This one is angle of incident. This one is angle of reflected. This one is angle of refraction. Okay, refraction, refracted angle. Okay, this one 90 degree also refracted angle. Alright. So this is total internal reflection. Okay, this is what I want you to see where the light can totally internal reflected, even though the glass is transparent, but the light cannot come out here. Okay, the light reflect inside. Okay. Alright. Okay, continue. Okay, refractive index and critical angle. Okay, relationship between refractive index and critical angle. Okay, so this is the refractive index. Refractive index equals to sine I. The incident angle must be in vacuum or air over sine R. Okay, R, this refracted angle, it must be angle inside the medium. Okay, it must be angle inside the medium. And then so because the incident angle is 9, because the angle in the medium, okay, this one because the angle in the sorry, not angle in the medium, angle in the vacuum or air is 90 degree. Okay, so it's 90 degree okay, sine 90 degree over sine C. C is the symbol for critical angle. Okay, C is the symbol for critical angle. Okay, that means the angle that is inside the medium is the critical angle. Okay, and then the medium, and then the angle inside the vacuum or air will be the incident angle. So we got discussed this previously okay, we got discussed this previously that this sine I over sine R, although this I is a symbol for incident angle, but this angle I must be angle inside vacuum or air. And then this R, although R stands for refracted angle, but this angle, it must be angle inside the medium. So sine angle in vacuum or air over sine angle in medium. So angle in vacuum or air is 90 degree when the angle in the medium is critical angle. So sine 90 degree equal to 1. So that means we can calculate the refractive index if we know the critical angle. Okay, 1 over sine C, critical angle, then we can get the refractive index of the medium. So that means until now, so far, we already know how many methods to calculate refractive index of medium. Okay, first, the original one, refractive index, is speed of light in the vacuum or air over speed of light in medium. This is the original equation to calculate the refractive index. And then from Snell's law, sine I over sine R. And then from real depth, apparent depth. Okay, real depth over apparent depth. Okay, so that means until now, total we have 4 methods to calculate the refractive index. So of course for the same medium, let's say glass, okay, let's say the refractive index of glass, don't care whether you use speed of light, you use incident angle, refracted angle, you use real depth, apparent depth, or you use critical angle, you will be able to get the same refractive index. Okay, you will be able to get the same number. Understand? Okay? Okay, so from here, the greater the refractive index, the smaller the critical angle. That means if the refractive index of the medium is bigger, then that means the critical angle will be smaller. So what does this mean? This means total internal reflection is easier to occur when refractive index of medium is greater. Okay, that means if the medium have a bigger refractive index, then easy to have total internal reflection. That means the incident angle no need to be very big. Then you can get total internal reflection already. So for example, that means like this. Let's say okay, you have this medium A and this one is air. Okay. So this one, like this angle, you already can get. Let's say okay, this one is 30 degree. The critical angle is 30 degree. So that means medium A, you need to increase the angle until bigger than 30 degree. The incident angle inside the medium A must be bigger than 30 degree. Then only you can have total internal reflection. And another medium B, this one is air. This one 45 degree, for example, then you get 90 degree. The light come out here. Okay, the critical angle for medium B is 45 degree. That means that the incident angle you need to increase until 45 degree, until more than 45 degree. Then only you can get total internal reflection. Okay. So that means that medium B is more difficult to achieve total internal reflection. Okay, get the idea. And then, okay, natural phenomena and application of total internal reflection in daily life. Okay, where is it that we can observe total internal reflection? So, for example, here we have a simple experiment. So here we have water and okay, there is a wooden block prop up the bottle, and then we use a laser pointer, point at this point. So at this point, we poke a hole and the water spurt out from the bottle. Okay. So if we point the laser pointer here, okay, if we point the laser pointer here, so the light should come out like this, right? But instead, the light follow the stream of water like this. Okay, the light, here is the total internal reflection. Here is another total internal reflection. So the light should come out, but did not. So the light, total internal reflect inside here, total internal reflection inside here. So the light follow the stream of water. onto the floor. Okay, I'll go inside the plastic basin like that. So the light then follow the stream of water like this. Okay. Okay, next. Okay, so this is the explanation. Okay, laser beam which enter the water stream has angle of incidence of laser beam travel from water to air greater than critical angle of water. Okay, that means the angle of incidence is greater than critical angle of water. So the laser beam experience repeated total internal reflection until come out from the end of the water stream. So if water stream is replaced by oil stream, light beam will experience total internal reflection more times. Okay, the reason is because oil have higher refractive index than water. So critical angle of oil is smaller than water. Okay, so here is the laser light. Okay, the laser light, and then here this is the angle of incidence. So this angle of incidence is larger than the critical angle of water. So the light experience total internal reflection. Okay, experience total internal reflection inside here and then here. Total internal reflection again, and then here total internal reflection, and go down. So for example like this lah. Okay. Alright. Okay, so for example here, okay, the refractive index of water is 1.3. So we can calculate the critical angle of water. So refractive index equal 1 over sine C, the critical angle. So let's try to calculate the critical angle of water. So 1.3. So the critical angle. Okay, critical angle of water is 50.3 degree. Okay, 50.3 degrees. So that means if this angle is larger than 50.3 degree, then it will be able to have total internal reflection. Alright. And oil, okay, oil have higher refractive index. So that means the critical angle is smaller. So that means the critical angle of oil will be smaller than 50.3 degrees. So that means this angle don't need to be as big as 50.3 degree. Okay. So if no need to be bigger than 50.3 degree, that means the total internal reflection can happen at a smaller angle. If it happen at smaller angle, then it can reflect more number of time. Okay, get the idea. Okay, so next we want to look at application of total internal reflection. Okay, so this is this is what is it that we can see in daily life if you set it up. Okay, next we will look at one application which is optical fiber. Okay, if you all have Unify use optical fiber or fiber optic okay, fiber optic cable for very fast internet connection. Okay, so optical fiber widely used in the field of telecommunication and medicine. So made from pure glass or plastic fiber, internal core which has high refractive index is surrounded by a layer of cladding with low refractive index. So the light signal enter one end of the optic fiber and experience total internal reflection continuously in the inner core until they reach the other end. As such, signal can be sent rapidly without disturbance from electric signal. Okay, so this inner core, have high refractive index. This outer cladding have low refractive index. So basically, this outer cladding is a material that represent or replace air. Okay, air. Okay, so what happens is when the light go inside, okay, go inside the inner core, then it will be able to experience total internal reflection. Okay, it will be able to experience total internal reflection multiple times. Reflect, 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 reflect like this. So that means the light signal, okay, can be used to transfer information. Okay, we can use light signal to transfer information, transfer data. You want to email, you want to watch movie, transfer file, okay, digital file, then we can use light signal. So basically, we use the blinking of the light. Okay, the light on and off, on and off, on and off, blink, 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 to form like a code. Okay, like a computer code, and then the modem, okay, the modem in your router lah, okay, will be able to read and translate this blinking of the light, okay, into a computer language, okay, and send into your computer so that your computer know what kind of information is coming in. Okay, and when you want to send information out, your modem also will change the electric signal into light. Okay, so it will make the light blink, 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 and then it will send your information as light. Okay, so this is optical fiber. So this optical fiber optical fiber is better than sending information using electric wire, because if you send information using electricity, then it can be disturbed from electric signal. For example, electric field, magnetic field, it can disturb or interfere with the electric signal. So it can make the file, that the computer file that you try to send will be corrupted, or a part of it can be lost. Okay, so optical fiber is much better. No interference from electric signal and magnetic field, and also can travel faster because it's light. Light have the highest speed. Okay, nothing can travel faster than light. Okay, the speed of light is the fastest in the universe. All right. Next is a Prism Periscope. Okay, used to see objects behind a barrier. Made up of two right-angle prisms fitted at both ends of a long tube. Light rays from an object travel along the normal to the side AB of the upper prism, pass through the opening of the periscope. The light ray reaches side AC without refraction. The angle of incidence is 45 degrees and is larger than the critical angle of the prism, which is 42 degrees. Okay, so this critical angle of the prism is the critical angle of the material that is used to make the prism lah. So in this case is glass. So this 42 degrees is the critical angle of glass. Therefore, total internal reflection happens at side AC and the light rays are reflected downward. So the refracted light ray travel downward along the normal to side DE of the lower prism. Once again, the reflected light ray experience total internal reflection at side DF. Finally, the reflected light ray emerged from side EF without refraction and entered the eye of observer. So the image form is upright and the same size as the object. So you look at here. So you see here the light from the object go inside. Okay, when it go inside, here it is right angle. So that means here is 90 degree. Okay, 90 degrees. So that is why there is no reflection. The light just goes straight in because the incident angle is 0. Okay, the incident angle is 0. So the light goes straight in. And then when reach this boundary, okay, this border between glass and air, so the angle, this angle is bigger than the critical angle. Okay, this is 45 degree. Okay, here this is greater than this angle is 45 degree. So that means it's bigger than the critical angle. The critical angle is 42 degree. Okay, so if greater than the critical angle, so the light will be able to reflect, totally internally reflect. Okay, so same with here. The light go in 90 degree at the border here. This is the normal. This angle 45 degree is bigger than the critical angle, which is 42 degree. So the light undergo total internal reflection. Okay, total internal reflection. Reflect down, and when the light come out here, go from the glass out, because it reflect 45 degrees, so that means here the angle will also be 90 degree. So this 90 degree is very important because when it's 90 degree, then that means the light will be able to travel straight out and the light will not bend. Okay, the light is not going to bend, the light will just go straight out. Okay, go straight out until down here there's another glass prism. Okay, the light go in until here, and again total internal reflection because the angle of incident is higher than the critical angle, which is 42 degree. So total internal reflection come out here, go into the eye. Here also same, total internal reflection come out, go into the eye. So this is what we call the Prism Periscope. Okay, the Prism Periscope. Okay, so the Prism Periscope is better than the Refractive Periscope or plane mirror periscope that is made from plane mirror, because the light undergo total internal reflection, so that means the image will be brighter because all of the light reflect down. Okay, all of the light reflect into the eye of observer, so the image will be brighter compared to if you use just glass, not glass, just mirror periscope. Okay, let's say that you have a periscope. So this periscope that is made from mirror. Okay, so we have a mirror here and also a mirror here. Okay, if this is just a mirror, okay, if this is a mirror, then the light reflect. Okay, the light can reflect, but the image will not be bright. Okay, the image will be less bright because the normal mirror, it can cause the light to scatter. Okay, it can cause light to scatter. So that means the light after reflect, some of the light do not propagate together straight down, but it spread to other area. Okay, spread in other direction. Okay, this is the eye. So this is the object. So if use mirror, got a few problems. Okay, first is the image less bright. This is compared with the Prism Periscope. This is compared with Prism Periscope. Okay, image less bright. Why the image less bright? Because because the mirror. Okay, how the mirror works. The mirror is like this. Okay, this is a piece of glass. And at the back of the glass, there's a layer of silver. Okay, at the back of the glass, there is a layer of silver paint. Okay, silver paint. Because glass is actually transparent, right now, the light can pass through the glass. But in order to make the glass be able to reflect the light, so we put a layer of silver paint at the back of the glass. So then the light can then the light will be able to reflect. Okay, and then we can have a mirror. But unfortunately, because of this glass, some of the light will reflect, in other direction. Okay, some of the light will reflect in other direction. Okay, that means from the surface, light can reflect, go to other direction. Okay, reflect, go to other direction. So it causes the brightness to decrease. Okay, brightness decrease because the light scatter to other direction. And another problem is you will be able to get overlapping image. Okay, if you see from here, the light go in, you have to pass through the glass, then only reach the silver pane, then only can reflect. But this surface of the glass is able to reflect a little bit of light because of the smooth surface. Any smooth surface can reflect light. That is why when you look at any like a glass, the glass is supposed to be transparent, but you can see your own reflection, a little bit of your own reflection on the glass. Okay, on the window, glass window, or anything, any glass. Okay, glass door, glass window, the window of the car, okay, the windscreen of the car, you can see your face on the mirror, not the mirror, you can see your face on the window, on the glass, right? So the reason you can see your reflection on the glass is because the surface of the glass reflect a little bit of light. Okay, reflect a little bit of the light. So this is what happened with the normal mirror. Okay, this is what happened with normal mirror. So the surface of the glass reflect a little bit of light. So you see, the surface of the glass reflect a bit of light, the silver reflect light also. So what happened is you have overlapping. Okay, the result is you have overlapping image. Okay, that means if this is the image, and then you can get another image. Get another image, so overlapping image like that. So this can decrease the clarity of the image, so the image become not sharp. Okay, not sharp, not clear. So this is two problem with using mirror periscope. Okay, this is a mirror periscope. Okay, this is a problem with mirror periscope. Okay, so why I explain this mirror periscope to you? Because question usually like to ask. Okay, if your question come out about prism periscope, maybe it will ask, what is the advantage of prism periscope compared to mirror periscope? So you have to know what is the advantage and disadvantage. Okay. Advantage of prism periscope is definitely better than mirror periscope. Okay, so this is the two advantage of prism periscope compared to mirror periscope. Okay, prism periscope can produce brighter image. Okay, mirror periscope the image is less bright, and prism periscope will not have overlapping image. Okay, no overlapping image. While mirror periscope can produce overlapping image. We can reduce the clarity of the image. Okay. All right. Okay. After this, cat's eye reflector. Okay, we all got see this kind of reflector on the road, right or not? Okay, when you drive a car, and you can see that this reflector produce light, but actually this reflector, it does not produce light. Okay, this thing at the road, okay, which is put on the road, it doesn't produce light by itself, but instead it reflects the light. Okay, so the light from your car, okay, will go in and then will undergo total internal reflection and coming out. So what you are seeing is actually the light from your own car. Okay. So cat's eye reflector. Why is it called cat's eye? Because if you see the eye of cat at night, okay, let's say you take a torchlight and then you shine your torchlight onto the eye of cat, you can see that the eye of the cat is very bright. The reason is because this is the same thing that happened, because the light from your torchlight will undergo total internal reflection inside the eye of the cat and come back out. So you can see that the eye of the cat is very bright, like got light come out like that. Okay, so that's why this is called a cat's eye reflector. Okay, so this is used for purpose of safety for road user at night. Okay, light ray from car headlight enter the reflector and experience total internal reflection on the back surface of the reflector. Okay, but of course nowadays there are two types of this kind of safety equipment on the road. We have two types. One type is this one, cat eye reflector. If another one is the one that it can produce its own light. The one that you see on the road and then is able to blink like that. That one is able to produce its own light. Okay, but you rarely see that one. The one that can produce its own light, blink, very rare. Okay, very rare to see. Mostly is this type, the cat's eye reflector. Okay, so formation of rainbow. Okay, how is it that the rainbow form? Okay, formation of rainbow is a phenomenon caused by refraction, dispersion, and total internal reflection when light passes through water droplet in the air. So figure 6.22 show the formation of rainbow. Okay, so ray from the sun come into the water droplet and then will undergo refraction. Okay, so this is the normal. Okay, this is normal. This is normal. Okay, so the light undergo refraction. And when the light undergo refraction, you see that the light undergo dispersion. Okay. That means the light spread out. The different color of light spread out. Why is it? This is called dispersion, dispersion of light. And you got learn about this in lower form science. If I'm not mistaken, in Form 1 or Form 2, okay, you got learn about dispersion of light. So why is it that the light will disperse? Why the light spread out? The reason is because, remember what we learned in the previous topic about electromagnetic wave. Okay, when we learn about electromagnetic wave, we learn that different color of light have different wavelength. Okay, different color of light have different wavelength. So red color, the wavelength is longer until blue or purple, the wavelength will be shorter. And we learned in the first topic about light, we learned that the red color light, when go into the medium, the refractive index, okay, the refractive index is, when you calculate, if you calculate the refractive index of the medium using red light, okay, you will find that the speed of light only decrease a little bit. Okay, that means when the red light go into the water, in this case go into water, the speed of light only decrease a little bit. That means the speed of light will be faster inside the water. Compare with purple light. Purple light, the speed of light will be lower when inside the water droplet. So if the speed of light become lower than red light, that means the purple light will refract more. That means it will bend more. Okay, if it bend more, that means the refracted angle will be smaller. This one, the refracted angle will be bigger. You see or not? Okay, so as you can see from here this one is the refracted angle of purple light. This one is the refracted angle of red light. So the refracted angle of red light is bigger. The refracted angle of the purple light is smaller, because the purple light, it bend more, it refract more compared to red light. So different color with different wavelength have different angle of refraction when go into the water. Some red bend a little bit, and then orange color bend more than red, yellow bend more than orange, green bend more than yellow, light blue bend more than green, dark blue bend more than light blue, and purple bend the most. Okay, bend much more compared to the dark blue. So when there's a case, when this happens, so the light will spread out, the different color of light will spread out. So this is what we call a dispersion of light. Okay, the light disperse, and then when the light reach here, reach the back of the water droplet. You see, this is the normal, this is the tangent, this is the tangent of the surface of the circular surface. This is the normal. So when reach here, it will undergo total internal reflection because this angle is bigger than the critical angle. Okay, this angle bigger than the critical angle. So what happens is all of the color, all the color, different color of light, it will undergo total internal reflection. Okay, and go on this surface, on the other surface of the water droplet. So when reach this surface, what happens? The light is the angle is smaller than the critical angle, so that means the light will be able to come out from the water droplet. So when the when the light want to come out from water droplet, again dispersion of light happen one more time. Okay, dispersion happen a second time because the different color of light, they are propagating at a different speed of light inside the water. Red is faster, purple is slower. So that means when they come out from the water droplet into air, the change in the speed will also be different. That means red light, when come out, it only become faster a little bit because red light is already fast. Okay, because red light when go into the water, it only slow down a little bit. So when come out, it only become faster a little bit. Okay, and purple, so from orange, yellow, green, light blue, blue to purple. Purple, when go into water, just now, when go into the water, it slow down more. So that means when it come out, it will become faster, more. Okay, the changes in the speed of light will be greater compared to red light. Red light only change a little bit, so the refraction, the change in direction is not much. But for purple light, because the change in the speed of light is more, so that means it will be able to bend more. The refraction of purple light will be more. So you can see that again the light will spread out more. Okay, it will spread out more. So purple will bend more away from normal than the red light. So when the light spread out like this, so the observer, the eye of the observer, it can see that the rainbow, a round rainbow, half circle rainbow. Okay, actually the rainbow is round. Actually the rainbow is one circle, but we only see half because another half is inside the ground. Okay, unless you stand. If you stand on the cliff, if you stand on the cliff, then you can see a round rainbow. Okay, you can see a circle rainbow like this. but we stand on solid, we stand on the ground, so we only see half of the rainbow lah. The other half is inside the ground. Actually, when I say inside the ground, it doesn't mean like actually inside the ground lah, okay? It's like blocked by the ground lah, okay? So it cannot form, okay? Get the idea. So then we will be able to see, this is also the reason why we see that the red light is at the bottom and then the purple is at the top lah. Okay, when we look at the color of the rainbow, the red is at the bottom and then purple is at the top. Okay, this is the reason lah. Okay, so this is formation of rainbow. Okay, so let's look at the explanation here. Okay, when white light from the sun enter water droplet, the light experience refraction and disperse into different color. All these different color experience total into reflection on the surface of the water droplet. So light ray reflected experience refraction and disperse again when moving from water to air. So color of rainbow are seen by the observer. So how is it that we can see rainbow? We must stand at the back of our back must face the sunlight lah, and then in front must have water droplet. Okay, that means if you see rainbow, that means in front of you there are water droplet. Maybe it just rain. Okay, or some far away places still raining. Okay, so you can see water droplet in the sky. Okay, there's water droplet in the sky in front of you, and then the sun is at your back. Okay, the sun is at your back, and the water droplet is in front of you. Then you can see rainbow. You can also make your own rainbow lah if you want. Okay, you wait for a day where there is no cloud. Okay, no cloud. The sun during early in the morning when the sun just rise up, or during the evening when the sun is setting. But the best is usually in the morning lah. Okay, in the morning the sky, the air don't have a lot of dust. So you can get more direct sunlight. Okay, you need a light that is moving straight in, and then you take a hose. Okay, and then you spray water. You spray the water into the sky lah. Okay, that means if you want to make your own rainbow, you want to see rainbow, you can do like this. During early in the morning, the sun just rise up. Okay, the sun just rise up, you stand here, and then you take a water hose, and then you spray water. You spray water in front of you. Okay, make sure the water is sprayed into a small droplet lah. Okay, you spray water in front of you. And then the sunlight from the back, it will undergo total reflection, and then you can see rainbow in front of you lah, and then you will be able to see rainbow. Okay, in front of you like that. Okay, so this is how we can see rainbow lah, like that. Usually in the morning lah. Okay, in the morning or in the evening. But in the evening, usually is more difficult lah, because in the evening there's a lot of dust in the air. There's more dust in the air during the evening, so more difficult to get a straight sunlight. Okay, and during the afternoon the sun is straight up, so you cannot see you cannot make rainbow lah, because the sun must be, the light source must come from your back. Okay, must come from your back, so you can see the rainbow here. Okay, get the idea? Okay, This one is formation of mirage. Okay, mirage. So on a hot day and bright day, a car driver see the blurry image of a puddle of water. Okay, looks like this. Okay, I'm sure that maybe you also got see this before. Okay, image of puddle of water on the surface of the road ahead. When he get nearer to the puddle of water, he discovered that the puddle of water does not actually exist. This natural phenomenon is known as mirage, which is caused by refraction and total internal reflection of light. Okay, so figure 6.23 show the process of formation of mirage. Okay, so you see how is it that the mirage is formed? Okay, so on a hot day, the layer of air that is near the road, okay, the layer of air that is near the road will be hotter because it's being heated by the road. Okay, so the air that is higher above the road surface will be cooler. Okay, so hot air is less dense and cold air is denser. So the hot air have lower optical density. Okay, optical density is lower. Cold air have higher optical density. Okay, higher optical density. So that means when the light, okay, let's say there's this cloud, you want to see the image of this cloud. The light from this cloud go from high optical density to low optical density. What will happen? That means the light will become faster, right or not? From high optical density is slower. Low optical density is faster. So the light become faster. When it become faster, it will refract away from normal. Okay, it will refract away from normal. So what happens is the light will bend. And when the light bend away from normal until the bottom here, the angle, the incident angle will become bigger and bigger until the incident angle is larger than critical angle of air. So when it becomes greater than critical angle of air, what happens? The light will experience total internal reflection. So it will reflect. So what happens here is total internal reflection. Okay, total internal reflection, the light will bend up. And then when it go up, the light will go from less dense to denser. That means from low optical density to high optical density. So the light will become slower and it will refract towards normal. So it will bend upward like this and into our eyes, into the eye of the observer. So when the light go into our eye from this direction, so from the point of view of the observer, it will look like the light come from here. Okay, it looks like the light come from here. So if it looks like the light come from here, then that means you can see the cloud here. Okay, you can see image of the cloud on the road. Okay, so you can see like there's a cloud on the road, there's a reflection on the road. So the logical thing is, how is it that the road can reflect light? Okay, how is it that the road can become like a mirror? The only logical reason is the road is wet, got water. So this is what our brain automatically tell us, because in nature, the only reason the road can reflect light, can reflect image, can form an image, is because there's water. Okay, there's water on the ground. Then only you can see reflection. Okay, so that is why we see something like a pool of water on the road surface. Okay, it looks like a pool of water. So this is something that our brain try to process. Okay, our brain try to process to be so that it look like a pool of water on the road. Okay, but actually, of course, there's no water lah. Okay. Alright, so look at the explanation. Okay, layer of air above the road have different optical density. The layer of air just above the road surface is hotter than the upper layer. Okay, so the reason is of course because the road surface is hot. So the air that is near to the road will be heated by the road. So the air that is near to the road will be hotter than the upper layer. Okay, the layer of hot air has smaller optical density than cold air. Okay, light which travel from upper layer to the lower layer are gradually refracted away from the normal. When the angle of incident is greater than the critical angle of air, total internal reflection occurs. Reflected light rays are then gradually refracted towards the normal and reach the eye of the observer. The observer will see the image of a cloud as a puddle of water on the road surface. Okay, like this. So if you have never seen this before, you can try to find a road that is straight. Okay, that is straight and very long, a very long and straight road. You just go and find a long and straight road. Okay, and then don't sit in the center of the road lah. Okay, it's very dangerous. You just sit at the side of the road. Okay, if you stand, if by standing you cannot see, you can try squat down. Squat down. Okay, you squat down, usually you can see, because if stand up, you are too high up lah. So the light maybe did not refract until so high. So if you squat down, you can see. Okay, you can see that looks like there's a puddle of water like that. Okay, so or if there's a car coming. Okay, if there's a car coming, okay, you can see the reflection of the car, okay, on the ground. Okay, like that. The reason is because the light band, okay, the light band refract and refract. Okay, the light refract and reflect under the total internal reflection band up like this, go into your eye. So you can see like, so from your point of view, it looks like the light come from here. Okay, from your point of view, it looks like the light come from here. Okay, so you see the image of the car over here. Okay, like that. So you can try this and see this for yourself. Of course, safety first. Don't suddenly you stand in the middle of the road Okay. Okay, it can also happen when it's very cold, especially on sea. Okay, if go to a place where the sea water is very cold, okay, in the north okay, the northern part. We know that the earth is curved, right? Okay, the earth is curved. Okay, the earth, our earth is curved lah. So that means if you are on the boat here, okay, if you are sitting in the boat here, and in the opposite side here, if there is a boat, you cannot see the boat. Because the boat is blocked by the curvature of earth. Okay, so you cannot see. This is your line of sight. You cannot see the boat here. Okay, you cannot see the boat. But what happens is, if this sea, the sea water is very cold. Okay, what happens is the air near the sea water will also be very cold. Okay, the air that is near will be very cold, and then going up, cold, and then warm. Going further up, the temperature is higher lah. Okay, but the air that is nearer to the surface of the water is very cold. So what happened is, light from this ship, okay, light from this ship, when go here, what happened is, the light from the ship go from very cold to cold. That means if very cold, that means higher optical density. This one here is lower optical density. Okay, so that means the speed of light will become faster when it go from higher optical density to lower optical density. So what happens is, the light will refract away from normal. Okay, refract away from normal. So when you refract away from normal, okay, refract away from normal, okay, refract away from normal, okay, the angle become bigger than the critical angle. If this angle is larger than the critical angle, so what happens? Total internal reflection will occur. So the light will reflect down. Okay, if the light reflect down, okay, and go into your eyes here, then that means you will be able to see this boat. Okay, if the light bend down like this, so what happens is, you will be able, from your point of view, you will see the image of the boat looks like over here. Okay, it looks like the boat, looks like there's a sea in the sky, and there's a boat here in the sky. Okay, that is upside down like this. So this is, so you imagine if this is something that was seen by ancient people, people from long time ago, if they see this kind of thing, what is it that you think they will think? They will think that there is a boat in the sky. Actually, the boat is here, but they cannot see because the curvature of the boat, but they see the boat in the sky. Okay, so they will make up story lah. They will think that they see a god, or okay, they will see, oh, there's a god that is sailing in there's another world, the world of gods in the sky, and they also sail, they also sit in the boat, sail like us, like that. So all kind of story will come out lah. So this is the kind of story that happen in the northern culture, for example, like the Norse, okay, the Norse culture, or the Vikings, Viking culture. Okay, you can go online and Google it lah if you are interested. Okay, so got story come out lah. So this is what happened, okay, for ancient people in the ancient time, olden time. They see all kind of natural phenomena they do not understand, and so they would think that this is something that is supernatural, okay, have something to do with God or ghost or something like that. Okay, but nowadays we can explain, or we know that this is just refraction and phenomena that has something to do with the light. Okay, let's look at exercise. Okay, figure 6.28 show the path of light which travel from air to a prism. Okay, A, determine the angle of refraction of light ray in the prism. Okay, angle of refraction of light ray in the prism. So this one, the light go inside here, 45 degree, and it says that the refractive index of the prism is 1.5. Okay, so we can calculate the angle of refraction. A sine I over sine R. Okay, so this is 1.5. So the incident angle, okay, you see, I know there is still 1.5 lah, but just to make it clear, this 45 degree is actually not this is not the incident angle. The incident angle, we must take the incident angle from here, but coincidentally, because it's 45 degree, so that means this angle here is also 45 degree lah, because this is 90 degree, right? Okay, so this one 45, so here also 45. Okay, so this is the incident angle. Okay, so it's still 45 lah. So how much is the refracted angle? Okay, so the refracted angle is 28.13. Okay, 28.13 degree. So that means the light come out here like this. And this angle is 28.13 degree. Okay, so this angle here is 28.13 degree. Okay, B, will the light ray experience total internal reflection at side A, B of the prism? Okay, so you see, we need to calculate the incident angle here lah. So here, this is the normal. So how much is this angle? Okay, how much is this angle? If this is 28.13, then how much is this angle? Here is 45, here also 45. Okay? Here 45, here 45. So we need to calculate this angle here, angle of incident. Okay, so if here is 28.13, because it is 90 degree, right? So that means here is, okay, 61, okay, this one here is 61.87 degree. This one is 45, 90, so here is also 45. So 180 minus, okay, so here is 73.13 degree. So this angle is 16.87. Okay, this angle is 16.87. Okay, so will it undergo total internal reflection? Obviously no lah. Okay, obviously no. Maybe okay. Will the light ray experience total internal reflection? No. Okay, explain your answer. Because the incident angle is less than the critical angle of the prism. Okay, less than critical angle of the prism. So we can calculate the critical angle of prism to prove lah. Okay, so this refractive index 1 over sine C is 1.5. So the critical angle will be 41.8 degree. So the incident angle is less than the critical angle of the prism. Alright? Okay, like that. Okay, Okay, number 2. Figure 6.29 show a fine optical fiber made up of inner core which has a high refractive index surrounded by cladding material of a low refractive index. Okay, A, determine the critical angle of the optical fiber. Okay, so what is the critical angle of the optical fiber? You see this is 1.8. Okay, this one the refractive index of the inner core is 1.8, and then the outer cladding is 1.4. So we can calculate the critical angle because we know the refractive index of the inner core. Okay, so n equal to 1 over sine C. So 1.8, 1 over sine C. So the critical angle the critical angle will be 33.75 degree. Okay, 33.75 degrees. So this will be the critical angle of the optical fiber. So what is the advantage of fine optical fiber? Okay, fine optical fiber. So first is advantage is flexible. Okay, flexible, can be bent without breaking. Okay, next is able to transfer information at the speed of light. Okay, that means can transfer information very fast. Okay. Okay, light signal not affected by electric and magnetic field. Okay, like that. So these are the advantages of fine optical fiber. Okay. All right.